Hello again, this is Math 2231, remote delivery, April 16th, 2020, and this is the Fundamental Theorem of Calculus,
Remember,
Part 2, and again,
I
use
told
keys
you
like this to perfect
about
your understanding. Maybe
in a video
especially
game
once
on
I had to
today's lecture.
take a bird with me to slay a dragon. In the same way, I warned you that don't forget about the antiderivatives that we studied because they will come back and save you from a dragon one day. That is the day. Today is that day. Okay, so here's the fundamental theorem of calculus part 2. Suppose that lowercase f of x is a continuous function on AB. This is part of the if part. You need this to use the theorem. And also suppose that capital F of x is any antiderivative. There are many, but we take any antiderivative. You see it as appearing in the theorem of lowercase f of x. Then the integral from a to b, the definite integral from a to b of lowercase f of x dx is equal to capital F evaluated at b, the upper limit of the integral, minus capital F evaluated at a, the lower limit. And this notation here means exactly this. That is the way you write that often in your work. The proof, I'm giving you the proof for completeness, but I'm not holding you responsible for reproducing the proof, but a serious student would probably read through this. I'll just make a couple of comments. The first is we're going to use part 1 of the fundamental theorem of calculus in order to prove this. And the other thing is we're going to use the mean value theorem, because the mean value theorem helped us know that if g of x and capital F of x were any two antiderivatives of lowercase f of x, they differ by a constant. And the calculation happens here. It also becomes apparent that it really doesn't matter what antiderivative I use, because the constant's going to subtract off when I do this calculation, so you might as well take the constant to be 0. Let's use this theorem to calculate an old friend, a problem we've done many times. So we're integrating from 0 to 2, x squared plus 1 dx. So here we're going to add 1 to the exponent and divide by the new exponent. That gives us this. Here we're going to add 1 to the exponent, divide by the new exponent, and we get this. We did it term by term. We're doing it at 0 and 2. I put 2 in. This minus sign is from the fundamental theorem calculus. Then I substitute 0 in here and I get that. And the answer is 14 over 3. Okay, so here are some examples I would like you to try, and we'll hit pause in a moment. The first one is an indefinite integral, so we're going to get a family of functions. We may get numbers for b and c. Let's see how you do. Let's see how you did. In the first one, I add 1 to the exponent and divide by the new exponent, getting this. In the second one, I add 1 to the exponent, divide by the new exponent, and I get this. Notice I'm dividing by minus 1, so that becomes a minus plus c. Now, the next two examples are definite integrals, going from here 1 to 2, so I get the same thing. Notice that I'm taking c to be 0 here. I substitute the value in for 2. This minus sign is from the fundamental theorem of calculus. And then I substitute 1, I do the calculation, I get 17 over 6. Now the last one could not be done because if I look at the graph of this, what I get is this kind of thing, and I have an infinite singularity at 0, which is within the interval of integration. This cannot be done using the fundamental theorem of calculus because this function is not continuous at 0. Here's some more problems for you to do. I encourage you to press pause, write these down, give them a go, and we'll look at the solutions in a moment. Let's see how you did. The first one, you should have gotten 84. The second one, you had to do algebra before you could do calculus because there is no product rule for integrals. So here you had to distribute this. You get x to the 3/2 minus 2x to the 1/2. Then you use your calculus rules. You get minus 32 over 15. And here was a calculation that happened in the midst of that you can do without a calculator. Here again, you had to do algebra before you did calculus, because there is no quotient rule for antiderivatives. So we divide w squared in here, and we get 2w cubed minus 1 over w, and it is plus 3, and that is w to the minus 2. We integrate all of those. We plug in the numbers. This minus sign is from the fundamental theorem of calculus, and we get 9 minus ln of 2. That is an exact number. In it, we use the fact that the ln of 1 is 0. And here, we could say that, oh, there's a constant of 1 here, and so the answer is going to be 1 times the length of the integral that you're integrating over, or you could do it the long way this way, but it's going to be minus 5, or minus 25. Minus 35, excuse me. Okay, here are some more problems for you to do. Please evaluate all of these. Press pause, do the work, and we'll see how you do. Let's see how you did. The first problem, we had to change the cube root of x squared to this, but then it is a straightforward calculation. Using the fundamental theorem of calculus, you should get minus 8 over 5. The next one was a trig thing, and again, I expect you to know this without using a calculator. And so we do it term by term using our properties for antiderivatives of trigonometric functions. We plug in, this minus sign is from the fundamental theorem of calculus. You plug the numbers in and you get this as your exact answer. Another trig problem. Here we do this term by term. The variable of integration is z. We get antiderivatives of this. We plug it in. This minus sign is from the fundamental theorem of calculus, and we do the calculation, and we get this as our answer. Now, some of my students might say that's the ugliest damn number they've ever seen in their life, but it is exact. It is the number, and you can get this without calculators. And so you might say, well, I haven't memorized the secant. Well, it's 1 over the cosine. And the last problem that we're doing is this one. Notice that if you have e to the minus z in the denominator, that is e to the z in the numerator. We factored out the 1/3, and so we get this. We do need to have the absolute value bars here for the logarithm, because when you plug those numbers in, you get minus 20 and minus 1, and so those aren't defined unless you take the absolute values of them. And this minus sign is from the fundamental theorem of calculus. And again, some students would say that's an ugly number, but there are no ugly numbers, just like there are no ugly babies. The last one could not be done for the same reason that this has t cannot be 0, and 0 is between minus 3 and 1, so this interval can't be done. You would get the wrong answer if you ignored what I said. Okay, here is another problem. Now, this is a piecewise function. It is y equals f of x is 6 if x is bigger than 1, and it's this other one if f is less than or equal to 1. And you want to evaluate these two integrals. Please hit pause, and we'll see how you did. Let's see how you did. Now, this is a piecewise function, so we do it in two pieces. We integrate here where it is continuous, and that's a point of discontinuity, so we have to have another integral. Now, for the first one, we're going from 10 to 22, so it's always defined to be 6, and so I can get the answer straight away. But for the other one, what happens is we have to break it into two pieces. We have to go up to 1, and then we go from 1 to 3 to calculate this one, because the definition of the function changes. And so here, when I do the calculation, what I will get is for the first one, I will get this. This minus sign is from the fundamental theorem of calculus on the first one, and this minus sign is from the fundamental theorem of calculus on the second one. You should get 72 and 21 for our answers. Here we evaluate this integral. The absolute value is here. Please hit pause. We'll see how you did. Let's see how you did. Okay, this is the graph, so it changes definition here. When you go up to 5/3, it is the negative of that, and when you go beyond 5/3, it is the positive of that. So we have to evaluate each of those separately, and we get 41 over 6. The last topic is even and odd functions. You might recall that if f of minus x is equal to f of x, and that could be like x squared or cosine of x, that's what is an even function. An odd function is x cubed or sine of x. Well, it turns out that if you're doing these and you're integrating over a symmetric interval, the integral from minus a to a of the even function is just going to be twice the integral from 0 to a. The reason you would want to do this is it's an easier calculation substituting in 0. Likewise, and the red function is an example of x cubed, if you go from minus a to a, it's going to be 0. And so if you have an even or odd integrand, you can exploit these calculation facts. So what I'd like for you to do in example 6, please, is do each of these, hit pause. We'll see how you do. Let's see how you do. So the first one, instead of plugging minus 2 and 2 in there and doing all the calculations and everything else, what you can do is change it from 0 to 2 because this is an even function. All the exponents are even numbers. Here the exponent is 0. So if you do the calculation, you can do it from 0. That's an easier calculation because when I put 0 in there, I just get 0. And you get one of my favorite numbers, 748 over 15. Here, this is an odd function, and sine is an odd function, so the answer is simply 0. Now more than ever, time is precious. Each day must count. Do the math. It will make you strong. And now, more than ever, take care of yourself and of each other. See you.